This is Section 5.1 of MA 104. We're asked to simplify each of these expressions, and if you look at numbers 17 and 19, you can see that 17 is a multiplication problem where we're multiplying factors with the same base. 19 is a division problem where we're dividing factors with the same base. For 17, to multiply factors with the same base, the base stays the same, and then all I need to do is add the exponents together. So I'll take the 3x minus 1 from the first factor and add that to the 4 minus x from the second factor, which if I simplify, the base stays the same. 3x minus x gives me 2x, and minus 1 plus 4 gives me plus 3. So this expression simplifies to 10 to the 2x plus 3 power. Again, for 19, I'm dividing two factors with the same base, so I just need to subtract the exponents. In this case, I want to remember that the 1 minus x is a single exponent. Even though there's more than one term, it's a single exponent. So when I simplify, I have 3 to the x minus the quantity 1 minus x. I'm subtracting those exponents. I have to remember my base stays the 3. I have x minus a minus x, so that's the same as x plus x, which is 2x, and then the minus also gets distributed to the 1, so that's 3 to the 2x minus 1 power. For number 21, I have a fraction that is being raised to a power. Both the numerator and the denominator of the fraction are raised to individual powers, and then the whole fraction is raised to the power of 3z. When I have a base that's raised to a power, and then that power is then raised to an additional power, I multiply the exponents. I'm going to do that for the denominator too. I have the 5 raised to the y, and then I raise that to the 3z. If I simplify that, 4 to the x power raised to the 3z power gives me 4 to the 3xz power, just multiply those together. 5 to the y power raised to the 3z power gives me 5 to the 3yz. My bases are different. I have a 4 and a 5, so that's pretty much all I can do with this particular expression. Finally, for 23, again I have the same base. My base in this case is e, so I'm going to be subtracting the exponents. I'm remembering to put the 2x plus 1 in parentheses. So I have e to the 5x minus the quantity 2x plus 1 power. If I distribute that subtraction sign, 5x minus 2x is 3x, and minus a 1 just gives me minus 1. In these expressions, I'm solving for x. In both of these equations, you can see that the bases are the same. Since the bases are the same in each one of these exponentials, the only way that these can be equal is if the exponents are also the same. So in each problem, I'll be taking the exponents and setting them equal to each other. For number 33, my exponents are 3x on the left. That has to equal the exponent of 4x minus 2 on the right. To solve, I'll subtract the 4x from both sides, which gives me the opposite of x equals negative 2. Divide both sides by negative 1, and x equals positive 2. For 35, when I set my exponents equal to each other, I have the x squared on the left. That's going to equal the 2x plus 3 on the right. This is a quadratic, so I need to solve it using one of the techniques we talked about for solving quadratics. This one does factor, so I can get it set equal to 0 by subtracting 2x from both sides and subtracting the 3 from both sides. That leaves me with x squared minus 2x minus 3 equals 0. Again, you could use the quadratic formula, but this one does factor pretty quickly into x minus 3 times x plus 1, and that will equal 0. I have two factors that are set equal to each other whose product is 0. One of those factors must be 0. It's either the x minus 3 that equals 0 or the x plus 1 that equals 0. If I solve each of these, I get x equals 3 or x equals negative 1. In each of these problems, it's a little bit different. For 37, my bases are not quite the same, but they're very close to being the same. The relationship between the bases in 37 is that they are reciprocals of each other. I have to have the same base. So what I will do is I'll leave that expression on the left as it is. I'll leave it as 4/5 to that 6x plus 1 power. To change the 5/4 to 4/5, I'm allowed to take the reciprocal of a base if I raise it to the -1 power. So now my bases are the same. By taking 5/4 and taking the reciprocal and raising it to the -1 power, I've made the exponential expressions equal to each other. Now that the bases are equal, I can set the exponents equal to each other. So I can set 6x plus 1 equal to -1. Solving that out, I can subtract the 1 from both sides. I have 6x equals -2. Dividing both sides by 6 gives me x equals, if I simplify that, -1/3. In 39, we're employing basically the same idea, just a little bit backwards from what we've been looking at. I have two expressions set equal to each other, so I have an equation. In this case, the exponents are equal. The exponents are each 5. The only way the exponents can be equal is if the bases are also equal. So I can set these bases equal to each other. I can set 1 minus x equal to 2x minus 1. If I solve that, I can subtract the 2x from both sides, which gives me 1 minus 3x equal to -1. Subtract the 1 from both sides, I have -3x equals -2. Divide both sides by -3, and I'm left with x equals +2/3. In each of these equations, I have to get the bases to be the same. In number 47, my bases are 25 and 125. I can rewrite both of those as powers of 5. 25 is just 5 squared. So instead of saying 25 to the x plus 3 power, I'll say 5 squared to the x plus 3 power. 125 is just 5 cubed. So instead of saying 125 to the x, I will say 5 to the third to the x. I have bases raised to an exponent raised to an additional exponent, so I can multiply my exponents together. If I multiply the 2 by this quantity x plus 3, then this becomes 5 to the 2x plus 6 power. I just distributed that 2. Equals, if I multiply my exponents together on the right, I have 5 to the 3x power. I've rewritten this equation so that my bases are the same. The only way the bases can be the same and then have the expressions equal to each other is if the exponents are also equal. So I can take 2x plus 6 and set it equal to 3x. The quickest way to solve this equation is to subtract the 2x from both sides, which leaves me with 6 equals x, or if you prefer, x equals 6. For number 49, my bases are 4 and 8. Both of those can be rewritten as powers of 2. So instead of saying 4 to the 2x plus 7 power, I will say 2 squared to the 2x plus 7 power. I'm going to set that equal to, instead of saying 8 to the x plus 2 power, I will say 2 cubed to the x plus 2 power. My bases are the same, so I can set the exponents equal to each other. But before I do that, I have to recognize that I have a base raised to a power raised to an additional power, so I can multiply the exponents. Same here, I have a base raised to a power raised to an additional power. I can multiply the exponents. If I do that, that gives me 2 to the, I have to distribute the 2, 4x plus 14 equals 2, if I distribute the 3, 2 to the 3x plus 6. Now that I have two expressions with the same base, I can set the exponents equal, which gives me 4x plus 14 equals 3x plus 6. I can subtract the 3x from both sides, which gives me x plus 14 equals 6. Subtracting the 14 from both sides leaves me with x equals -8.